should be acutely aware that in most of the cases these assumptions are likely to be violated. And yet we would like to explore some such kind of a relationship, which kind of a caution that needs to be exercised, what kind of a correction to the data that needs to be made, if at all we are going to use this distributor. It's something which is highlighted when looking at the non-fulfillment of these properties which we presume. This is the reason why we start with assumptions. For example, the most frequently quoted assumption is the nature of a return. Typically, most of the textbook would say that random term, that is the factor that we apply in a model like this, is going to have certain statistical behavioral properties. What are these? They are supposed to have a mean, which is 0, and they are supposed to be coming from such kind of spread around that 0, which is called fixed variance. Having this fixed variance is in fact what is called homoscedastic. Both of these spellings are valid because C is in fact K in Latin. So this is homoscedastic and heteroscedastic. What does it mean to have homoscedastic variances? Homoscedastic variance would mean that any UI, that means suppose I have one y1 x1, y2 x2, y3 x3, and so on. For each of them there is going to be some u1, u2 which is going to be operative and is going to affect y values. They are coming from this distribution means there are several possible values of u1 which can occur. Suppose for a moment, just think of it as a hypothetical experiment, and I can get any kind of a value as u1 belonging to this distribution. But what is the property that is going to have? It is going to have 0 mean. Meaning there are all possible u1s taken together, and if you take an expected value, it will be 0. If I consider all possible u1 and calculate their variance, what is going to be the variance that you are going to get? It is going to be same sigma square. Same for u2, same for u3, and so on. So, whenever we are going to deal with a property such as u1, u2, u3 belong to some such distribution where their variances are same and their mean is same, namely 0, then this kind of a property becomes handy to prove the two desirable properties that we aim to establish, namely unbiasedness and the minimum variance. Therefore, in this sense, fitting regression line using OLS is in fact really describing the behavior of the error term. Because what is not observable? It is the error term which is not observable. Y is anyway observable, X is anyway observable. But they don't go along the same line. So we imagine a line and fit it. But the nature of random term which is forcing Y to behave differently, and that's the significance of what we derived earlier in the numerical example, that there is an observed Y, and after fitting the line, there is something which can be called as an estimated Y. The difference between them is due to this. And when we do this, we can go back and check whether this assumption is true or not. And that's the key to the entire exercise of doing modeling with the help of regression equation. So in order to understand this, it is very important to understand what is the role played by u1, u2, u3, un, but they are not observable. But nonetheless, it is possible to make some kind of a conjecture about them and find out whether that conjecture is a realistic one, is it a valid one, or if it is invalid one, in what way we are going to tackle that violation of an assumption like this. And usually a term which is used for this is called IID, and this term really means whether it is u1 or whether it is u2, whether it is u3. When you make a drawing of a sample of the random term, they can take many values. That's the meaning of distribution, because it's not one fixed value. The values can vary, but in what manner are they going to vary? So for example, if I am going to draw a picture of either u1 or u2, it is going to be identical, because both u1 and u2 realizations are going to be spread around the same mean, say u bar equals 0, u bar equals 0, and if I look at the variability, this variability is same thing as sigma square. This is what we mean by taking the realization of each of the random shock containing separate distinct values of y being uniform. This is not our claim This is our claim to first explore what kind of random factors are actually observed and present in the data. Having observed that, we should in fact isolate those random factors, just as we did with a numerical example, and then ask the question, are the U1, U2, U3 of the type going to be of the same type? Meaning thereby, do they have same mean, say 0, and same fixed variance? In fact, getting same mean 0 is something which is naturally, inherently assured by the OLS procedure itself, that their mean will turn out to be 0. But is that enough? That's not enough. Why is it not enough? Because we are also interested the way in which random factors forces Y to behave, and the behavior is not really around, is not at the mean, but around the mean. Around the means implies that their variability as captured by the variances must remain same. If it does not, there would be natural obvious reasons for this. In what sense they are natural and obvious? They are obvious in the sense that, for example, if U1 and U2 are related, then by the very property of variance, what do we get? The variance of U1 plus variance of U2 plus covariance between U1 and U2. It is only when this term is 0, then these are independently additive. In fact, there is a slight problem here in the sense that if U1 and U2 are probabilistically independent, their covariances would be 0, but not other way around. The covariances might be 0 even when they are not necessarily independent. But with that caveat, one should be aware that pooling together variances is something which is possible by simply adding them if and only if the variability is devoid of any covariability. This covariance may be plus or minus. They might be negatively related, they might be positively related. And therefore, modeling of this type is equally modeling of error terms. That means we are not modeling Y alone with the help of X. We are modeling with Y one major component of Y about which we should be concerned, namely the random component contained in Y. And when we can isolate that credibly, and when we can make an usual statistical inference procedure that we will subsequently see, when is that valid depends on the nature of covariability as well. And that's the reason why you need an assumption which is called zero autocorrelation between any one random factor with another random factor, say 5th and the 8th. All these must have covariability which should be 0. And that's what we mean by saying that there is no autocorrelation. That means the error terms are not related among themselves. So there are two important assumptions. One is we believe that they all come from the same degree of variability. That means they have got the same variance, and this is something which is in fact in technical jargon called homoscedastic variance. That means their skedastic means being scattered, and they are scattered in the same manner, in the same degree. It's something which is homogeneous. That means that's the reason why you call it homoscedastic. If they are differently scattered, then you call it to be heteroscedastic, where hetero means different or distinguished, as against homo means of the same genre. And there were three kinds of claims which are usually made. A, that they come from the same distribution, meaning thereby they have same mean, same variances, they have zero covariances, that means zero autocorrelation. And same variance would mean that the degree of variability associated with U1 as against associated with U10 will be the same. What if, suppose variance associated with U1 is 5 and one which is associated with 10 is going to be 10. So in that case the variances are not equal. And as we proceed and as we derive these equations, it will become clear why making these kinds of assumptions to claim and establish the unbiasedness and the minimum variance property of the OLS is very easy to demonstrate and prove. In reality, it will not be so. If it is not so, we need to make some correction. What correction do we make? What kind of a diagnostic do we apply to check whether these assumptions are valid or invalid? That is something which we use, which is usually discussed in the subsequent chapters of the econometric textbook, which is usually called violations of OLS assumption. But before you understand the violation, one should first understand what kind of a picture in mind with which we start, so that we have something to compare with, so that we will be able to detect in which sense, in which direction, and in what way these violations are going to affect our estimation, which is based on the OLS formula. This is the purpose, and one elegant way of understanding this is to look at a very small sample, and a very small sample of u, very small sample of x, that means fixed values of x together with the random factors which operate with very small samples, so that you will be able to understand their significance. Combined with this, we are also going to look at the possibility which I had in fact posed as a question in the earlier lecture. What if I define some kind of a b, or say call it a beta, where I put it, the estimator will be like this. Typically in OLS we are going to subtract this component. Similarly in the denominator we are going to subtract this component. What if I don't use these components in the numerator and denominator? It would still remain in some sense linear. As you can now see, I can put even this as a linear combination of y values, because I can put xi. Please note, when I demonstrated linear property of OLS, I was using deviation. Instead of deviation, now you will have the original observations like this, and this will be used as weight, and I am going to take a solution. So this still continues to be a linear estimator. So this is an example of another linear estimator. Only difference being to use the older statistical languages, because these days you don't find this kind of a terminology used in the econometric test. This is not corrected for the mean or the means, and this is also is not corrected for the mean. What if I get an uncorrected data? I still get the idea of a linear estimator. Why is this estimator inferior compared to OLS? Alternatively, why do we think OLS estimator with deviation small xi divided by summation small xi square as a better estimator than this estimator? That means what role does the correction factor actually plays when we stack them off from the numerator and denominator? Is the way of comparing two estimators. And if I am able to show that the variability which results from this estimator as against this estimator happens to be different, and in that case, if the variance associated with this OLS estimator happens to be smaller than this estimator, then I am claiming that any other alternative linear estimator is going to be inferior compared to the OLS estimator. To understand this, it is very important to understand both these components of the argument, the role played by the nature of random terms, their covariances, their relationship and the interaction they have with respect to x on the one hand, and on the other, we will also look at how given this nature of error terms, in what sense any other estimator such as this, when compared with this, turns out to be more efficient in the sense of having low variance than any other claimed alternative linear estimator. In order to highlight this, we are going to look at two problems which are in fact there in Johnston and Dinardo's textbook, and it's a very instructive kind of a problem.